Hi, welcome back to Kin 3030 online. Today we're going to talk about static equilibrium at a whole body level. But just a reminder that last class we were talking about the center of gravity and how you would calculate it in a body, particularly that segmental method where you could find the center of gravity of the different body segments and then combine those center of gravities using a weighted average to find the center of gravity of the whole body. And we talked about how important that was in biomechanics. And just to talk about how important that would be in biomechanics, I'm just going to talk about a few scenarios. First, you're working with high jumpers. It's a pretty important one. They know and they want to know more about the biomechanics of their jump. Is the human jumping an example of projectile motion? Yes. We know that as soon as we take out, assuming we're not in a high air resistance location, once we're in the air, we are a projectile. And the part that follows that center of gravity is, again, that follows that projectile path is our center of gravity. So the question is, can a person, a high jumper, a skilled high jumper, cross the bar without their center of gravity crossing the bar? And the answer is yes. A skilled high jumper, in order to do it, first of all, what's going to knock over the bar? The knocking over the bar is the bar being hit by our body part, right? So if a body part hits the bar, then it's going to knock it off. So in order for the high jumper to get over the bar without their center of gravity going over the bar, it means the center of gravity actually has to be outside of their body. And a skilled, if you're doing this kind of flop, and I can't arch my back quite enough, and certainly without bending my legs, but in a skilled high jumper, as they go over, by arching their back, they can actually move the center of gravity of their whole body to outside, just outside their body. And so even though they are going over the bar, the center of gravity might actually pass through or even under the bar as long as they were arched enough. So, today we're going to talk about equilibrium and apply it to the whole body. Next class, we're going to very specifically talk about how that is applied to a specific joint. So, an example that we're going to tackle at the end here is a person drilling against a force gauge, and we want to know what the magnitude of the ground reaction forces are in this particular case. We'll come back to it. So, equilibrium. What is equilibrium? Equilibrium is a state characterized by balanced forces and torques. Balanced forces and torques. Really important. Now, we've actually been doing it in many of our sections up until this point, in muscle, in just looking at how muscles work around levers, even the idea of a teeter-totter. We're really looking at that idea of equilibrium. But now we're going to really put in equation words what it actually means. So the sum of all the vertical forces equals 0 for us to be in equilibrium. The sum, again, adding up all of the vertical forces acting on a whole body has to equal 0. In the sum of all the horizontal forces acting on a body have to equal 0. And all the torques, the sum of all the external torques acting on the body have to equal 0. external forces. Remember, external forces and external torques. We are not talking torques in, if I'm looking at the whole body, I'm not looking at within a joint, because of course both torques and forces come in those pairs that will cancel each other out. So sum of forces equals 0, and the sum of torques equals 0, but Newton's second law says the sum of forces equals mass times acceleration. Well, the mass isn't 0, so therefore to be in equilibrium we have to be in a situation where the accelerations, both linear and angular, are 0. There are two basic, I will also say, just to back up there, some of the problems you'll see us do, remember, acceleration equals 0 means you could still actually have a velocity, just a constant velocity. Hard to have a constant velocity in human movement where for all accelerations and torques. However, we will use as a code word for it a slow movement. And when we talk about a slow movement, we are basically saying that the acceleration is quasi-static, as we would call it, because the accelerations are so low that we could then use it as equaling 0. So typical problems that we solve here, two basic types. One where we know there is no accelerations, it is in equilibrium, and we know most of the forces, and we need to calculate a missing force. So sum of forces equals 0, as long as we know that it equals 0, meaning the acceleration is 0. And then we can say the sum of forces, and as long as we just have the one force missing sort of thing, we're good. The other one is where we know what all the forces are, and we want to check if it is in equilibrium, meaning the acceleration actually equals 0. So, a lever in equilibrium, we showed this. How do we know this lever is in equilibrium? We have our 15 Newton weight acting 40 centimeters from the axis of rotation, and on the other side we have our 60 Newton weight acting 10 centimeters from the axis of rotation, and in both cases they're going to create a 6 Newton meter torque, one clockwise, one counterclockwise. If you add those together, one will be positive, one will be negative. They will cancel each other out, which means it equals 0. So the sum of the torques around that axis of rotation equals 0. What is the actual force on the fulcrum? Sum of the forces equals 0. So if we know, it's not going up and not going down, it's perfectly balanced, it's not going up, going down, then the sum of the forces in the y direction are going to equal 0. Well, we know one is 15 newtons down, so negative 15 newtons. One is 60 newtons down, negative. And that leaves the F force of the fulcrum pointing up. And so F at the fulcrum minus 60 minus 15 equals 0. The fulcrum force has to equal 75 newtons. Now, we took our torques around the fulcrum. That's a very logical place to do it. It's an axis of rotation, just like our joints are axes of rotation. But we might not always want to take it around a particular joint for certain reasons. I'll tell you right now. In human movement, when it's dynamic, we actually have to take our torques around the center of gravity. It's a very common place that you have to take your torques around. So instead of an axis of rotation. So is it going to still show us that we're in equilibrium? So let's try a different point. Let's try from underneath the 15 Newton box. Well, now the torque being created by the 15 Newton box is 0 because it has no moment arm, 0 moment arm. There's the force of the fulcrum, which is going to be 40 centimeters times the force on the fulcrum, which is 75 newtons. We just calculated it. And the force of the 60 Newton box in the opposite direction, it'd be negative clockwise, times 50 centimeters, because it's 40 plus 10 centimeters from B. And it turns out, in this case, you have the 30 Newton meters one way minus 30 Newton meters the other way. They'll cancel each other out, sum of, and you will be left with 0. So it still shows that we're in equilibrium. If you are in equilibrium, different if you're not in equilibrium, but if you are in equilibrium, regardless of where you take your torques, you will get 0. So, some procedures for solving problems in statics. Number 1, state the problem in terms of mechanics, things you can measure. Draw that free body diagram, because clearly in this situation, you need to know where the forces are acting. You need to know what forces there are and where they are acting. And then you need to apply your appropriate equations of equilibrium and solve if possible. If possible means that you don't have too many unknowns usually. You can really only have 3 in two dimensions, like we're showing here, where you have an x, forces in the x, forces in the y, and a torque around an axis. 3 equations, 3 unknowns to solve. And then always interpret back in terms of the real problem. So, again, for static equilibrium, the forces need to be balanced, and in both the x and y directions, and the torques need to be balanced regardless around which point you take them around, which means you have these 3 equations in 2 dimensions. Next, we need to know exactly what forces are acting on the body and how they act and what direction, where they are applied. Where they are applied is important if you're going to get torques. So let's do that using the good old free body diagram. That's just a review of the steps for figuring out a free body diagram. And we have our common forces: gravity, friction, normal forces, the ground reaction forces of both a rough or slippery surface, which in the rough case include friction and a normal force. Forces that are rope-like in nature, like muscles, like holding on to a rope, and fluids. So let's look at an example of somebody climbing a wall. Let's create the free body diagram of them climbing a wall. So, isolate the system of interest. The system of interest is the person climbing the wall. It is not the wall, it is the person climbing the wall. So we have our person. And the next thing we want to do, we can see gravity clearly in this view, so we want to put the gravity force at the center of gravity of the whole body. Not the individual segments, we are looking at the whole body, so we want the center of gravity of the whole body and the weight of the whole body. Then we're going to look at the interaction with the environment. This person has, as they're climbing, let's say you were looking at somebody who climbing at a climbing wall. You created a climbing wall where every hand and foot hold will measure the force both vertically and horizontally, so that you can learn about how people climb and what forces, eventually maybe what finger grip forces you need to have and things like that. But in the first place, you need to know what forces are on their hand and how much they put on their hand, how much they put on their feet, maybe as a function of the different types of climbing holds and things. So you have a wall made of climbing holds, and each one of them measures a horizontal and vertical force. And they're all designed just like a force plate on the ground. They have a force that will give you zero. In one way, it will be positive. In the other way, it'll be negative. So all the ones pushing up, if you're holding on to a hand or foot hold, and you are pushing down on it, which means the handhold or foothold is pushing up on you, that is the situation where the force will give you a positive value. If you are pushing to the left, as we're looking at it here, pushing to the left, so that you see that I'm in line, that means that the force is pushing to the right, and it's going to give you a positive value. And that's going to be the same on all hand and foot holds. Now, you might not always be pushing to the left and the handhold pushing back on you to the right. Sometimes you might pull the other way, in which case that's fine, no problem. You're just going to put on your free body diagram what would be considered positive. And when you take the measurements, some of those actually might be negative. And no problem. Negative just means that it's acting opposite from the direction that you've drawn your arrow here. And then we, of course, add our reference frame. So, you have somebody climbing at this instant in time while they're doing this climb. These are the forces that are being recorded from the four different hand and foot holds. When it's zero, it means there's actually zero force in that particular direction. And when it's positive, it means it actually is exerting a force in the direction as drawn. And when it's negative, as it is on the right foot, it means that they are actually pushing in the opposite direction. So in that case, the minus 11 would be the person is actually pushing out to the right with that foot, which means the force, the actual foothold, is pushing to the left. Again, we're not going to change the free body diagram. We're going to go with the arrows we drew because that's what is recorded off of our hand and foot holds. But we just know that negative means it's acting in the opposite direction. So, let's start with the question, is this person in equilibrium? So the sum of the forces in the y direction, let's add up all the ones in the y direction. We have plus 9, anything where the arrow happens to be going positive based on our reference frame, we will add into the equation. Anything that is going negative based on our reference frame, we're going to subtract from it. So we have plus 90, plus 100, minus 740, because that's going down, plus 300, and plus 250. We add all those up, subtract off the 740, and guess what? It equals 0. So from the perspective of the y direction, we're not accelerating. Let's look at the x direction. The sum of all of those forces in the x direction. Well, we have a 0, we have a plus 1, we have a plus 10, and we have a minus 11. We add all of those up, and subtracting off the 11, we're going to end up with 0. Again, that means when we add up all the forces in the x direction, it's going to be 0, which means no acceleration in the x direction either. That leaves us with the last one, which is the sum of the torques around some point in the body. It's going to equal 0. We're going to use the center of gravity. As I said, the center of gravity is often used in certain types of studies, and particularly ones where they're not in equilibrium. So we're going to use that center of gravity as our axis of rotation, and we have to take every force, there's 9 forces there, and consider what is its rotational effect around that center of gravity. We'll start with the 740 that are acting at the center of gravity, and guess what? It has a moment arm of 0, so we don't have to worry about it. So it leaves us with the other 8. And in each case, we are going to look at the force and look at which direction it would rotate a system. So if I put a pencil over top of this free body diagram and I held it in place where their center of gravity is, and then I moved it so the other end was over top of where the hand or foothold is, and then I push in the direction that the force is acting, I can see if it's going to rotate it positively or negatively. If it's going to rotate it counterclockwise, which based on my reference frame I say is positive, or clockwise, which would be negative. So let's start with the 0 force one. Where it is, if I pushed on it, it would actually rotate clockwise, so it would actually be a negative, but there's no force there, so we really don't have to worry about it. That's the it would have 0 force, so it's not going to be one that we have to worry about. So next we have the 100 newtons that are acting on their right hand. It's pointing up. It's going to try and rotate them counterclockwise. So plus 100 times the distance that is from the center of gravity to where that is, and you can actually get that from the x coordinate. If you were digitizing this, you would know what the y coordinate. You would know what the x coordinate is of the center of gravity. You would know the x coordinate of where the hand is, and the difference between those would be the perpendicular distance of a vertical force. So vertical forces, the perpendicular distances are x's, and horizontal forces, the perpendicular distances are y's. The 1 Newton is also going to be a negative because it's going to try and rotate us clockwise. The 90 newtons is going to be negative because it's also going to try clockwise. The 300 newtons will be negative because it's going to try and rotate clockwise. Make sure for each one of these forces, you put your pencil over top of it and push it, hold it in that axis, and push it in the direction it is, where it's located, so you can see that it rotates it clockwise or counterclockwise. So the 10 Newton force, for example, is going to rotate counterclockwise, so it's going to be positive. And the 11 Newton one, that's a bit tricky there, because as we drew the arrow, it's going to rotate it counterclockwise, so it would be positive, and you can see that positive in there, but then you're going to put a negative in the actual magnitude of the force. So even though the arrow is positive, it will automatically end up as a negative torque because it is because the magnitude is negative. So you add up all your torques from all of your forces, and when you do that, it ends up being 0. Of all the things we do in this course, mathematically this is not difficult math because each one is just a torque, it's just a force times a distance, but it's a lot of different, just keeping track of everything. It is just a question of keeping track of it, and not every question is going to have 8 different forces acting on the hands and feet. Often when we're walking, we might have one under one foot, one under the other foot, or we're hanging from something, so we don't have anything under the feet. But I just want you to see an example where you actually see them under both the hands and feet. As I said, forces that go clockwise are going to be negative, torques that are clockwise will be negative. Torques that are counterclockwise will be positive based on our reference frame. And we didn't include the center of gravity because it has a 0 moment arm. It acts right at the center of gravity. So in the end, we can say that this person is in equilibrium because the sum of the torques around the center of gravity equals 0. The sum of the forces equals 0, and the sum in the x direction and the sum of the forces in the y direction equals 0. So we have a problem to solve. A person drilling against a force gauge. It shows that the force exerted by the drill is 100 newtons horizontally. So they're pushing with the drill horizontally. There's a force gauge here, and we measure that it's 100 newtons being pushed back on the person. The weight due to gravity of both the person and the drill combined is 800 newtons, and the location of the center of gravity is shown. If the person is not moving, so we know they are in equilibrium because they are in a fully static pose, that by definition is 0 accelerations. What would be the magnitude of the ground reaction force and the location of the center of pressure? So, we draw the free body diagram. You see the ground reaction force, the 2 components of the ground reaction force underneath their foot. We choose a place that we're going to consider 0, and we're going to consider it along the ground there at their ankle is our 0, 0. That just lets you know that is where it is. So that's where we're going to take our D from, our center of pressure. We have our 3 equations of equilibrium, extremely important. Sum of the forces in the x direction equals 0, in the y direction equals 0, and the sum of the torques around some point equals 0. In the x direction, we have 2 forces. We have the ground reaction force acting in the positive direction. We have the force on the drill acting in the negative direction. And all that equals 0, which means that the ground reaction force of the x direction, which would be the portion created by friction while you're standing on a horizontal surface, is 100 newtons. In the y direction, we have 2 forces. We have the ground reaction force, that push component, going straight up into the foot, which is the y component, and we have gravity acting down. So, and all that equals 0, which means the force of underneath the foot pushing up is going to equal the force going down, or the force due to gravity, which is 800 newtons. So 800 newtons up, 800 newtons down, cancel out, and we have 0. And the torques around the ankle. If we take torques around the ankle, we have 3 forces that we are worried about. Now, this is on the floor just below the ankle, so we don't have to worry about the ground reaction force in the x direction because it has 0 moment arm. We have the ground reaction force in the Y direction, which is 800 newtons, acting up, and times that actual center of pressure distance that we're looking for, how far in front of the ankles that is. And that's going to try and rotate the person counterclockwise. So it's going to be positive. And then we have the force on the wall onto the drill, and it's going to push this way. So again, they're going to rotate counterclockwise. It's going to be positive, and it's going to be multiplied by the distance from the ground up to where that drill is. That's the 1.1 meters. So 100 times 1.1 is that torque. It's going to be positive. We have the weight of the body. It's in front of the ankles, and it's going down. It's going to try and rotate the person clockwise. So it's going to be negative, and we're going to use the the x coordinate of that center of gravity, which is the 0.2 times that 800, and again, that'll be negative. So we have three components, one negative, two positive, and one unknown. That is the that distance from the ankles to where the center of pressure is underneath the foot. If we solve for that, we will end up with 0.0625 meters or 6.25 centimeters. So it will be underneath the foot. I'm going to leave this example for you to play with, but it is here for you to work on. And it comes with the frictional component.